Thank you for your kind introduction and uh, very good afternoon to all of you. So, for about next hour or so, I will take you through a journey in computer vision with a focused aim of detecting cancers, and we will focus on lung nodules and brain tumors, which are respectively precursors of lung cancers and brain cancers. And we will mostly work on or discuss really problems related to segmentation, like how you extract really the nodules or like the tumors, and then how you classify. So whether you want to classify as like benign or malignant, or certain like degrees of malignancy can you decide upon, and so on. And also, a part of the talk or the journey would be through many seasons, as you can see from the title, like a tale of many seasons. So, where I will emphasize that how the journey of computer vision kind of evolved actually for cancer detection. Well, I mean, this is with particular relevance to what we have been doing in our group. So, I try to categorize really the problem solving as a mapping to different seasons. With you will see like kind of interesting reasons. So with this brief introduction, let's straight away go to this talk, and I would start with an acknowledgement. I heard this talk given by Professor Venu Govindaraju at Sunnyva Fellow, from Sunnyva Fellow, at one of the premier conferences in India. It's CVIP, Computer Vision Image Processing, which is endorsed by International Association for Pattern Recognition. And he has a title like where he was in general talking about like the journey involving different seasons of artificial intelligence, so the 4 seasons of AI. But the inspiration of this talk definitely draws a cue from the talk given by Professor Govindaraju. But we will focus on a very particular journey, and it just happens to be that the titles have some similarities, but still, of course, I want to acknowledge Professor Venu Govindaraju. So this is the plan of the talk. So I will talk very briefly about our university and what we do in our research group, and then we will directly go to really the different seasons. So we will start with the first season, which is which I call, or which I map it to an autumn, like where we will focus on really classical solutions, and typically we'll be picking like 1 or 2 problems from different seasons. So this is really before the advent of deep learning. Like we still try to solve problems classically using let's say PDEs, for example, level sets or graphs, hypergraphs, and so on. Then we will see that there will be some definite developments necessary to make really more progress, and that I call as kind of a winter, where we will probably pause and we will see that some more developments are necessary to continue this journey of computer vision. So I just put like this deep learning brewing. The third season is mapped to spring, where we have like many flowers blossom. So we will combine like the deep learning with some classical solutions, and we will show again the goal is same, like so detection of cancer based on computer vision, but now the traditional techniques of computer vision will be empowered by deep learning. And then the final season would be like a rainy season, like where we will see that deep learning will probably rain, or you can say deep learning rains, and we will discuss 2 different problems involving classification, but they are mostly based on deep learning. Though we have these graph convolutional networks, but still it's like mostly dominated by deep learnings, and then we conclude. So that's the kind of plan. So since I come from a very different part of this art, then really thankful to Professor Krishna and Professor Dilip for inviting me here for a 1-month sabbatical. So I just put a small slide and a nice picture of our university. Like, we have two beautiful sprawling campuses, like, and all of you are welcome to visit there in Kolkata, the city of Mother Teresa, and also like a place like from where more than one Nobel laureates were born, including like Rabindranath Tagore and Amartya Sen, and Abhijit Gangabardhan, and so on. So in our university, we have mainly three faculties of engineering, science, and arts, but then we also have a set of interdisciplinary schools and a number of centers for studies. We offer like bachelor's, master's, and doctoral degrees, and you are more than welcome to browse. Like, as Prof. Krishna already mentioned, that it's like one of the highly ranked universities in India with a lot of potentials. Now, what we do, like this IVPR, is in an acronym for Imaging Vision and Pattern Recognition, and the group like which I formed after going back to Jadavpur University. So the broad area of interest is computer vision and pattern recognition, and we try to blend really like theory and applications. So the main thrust areas are like biomedical image and signal analysis, but we also do some works in multimedia, surveillance, security, and then there are like certain miscellaneous areas. Like from time to time, we continue to do works like which can be of pure theoretical interest or like very different sensors. Like for example, this neuromorphic vision, which is an event-driven camera. Like so, it's very different from the normal camera, and then we have been doing also some work over there. So I just like include some examples, like actually typically one example from each of these like four branches of the tree which I have just shown in the previous slide. So the first example is like an fractional anisotropy map of a DTI scan, which is obviously in a biomedical domain, and this was like the work like which we have been doing, which have been published in Expert Systems and Applications in 2021. So the goal here is to classify Alzheimer's disease, right? So how you find out like different classes of Alzheimer's disease where a person has an Alzheimer or not only that, like if the person has Alzheimer, to what extent the person has Alzheimer. So for that, like we use like this diffusion tensor imaging scans, and then also mixed like machine learning and deep learning techniques. The second example is very different from the domain of multimedia. So this was like a figure from our published paper in IEEE Transactions on Image Processing, where like we show how you can find out like multiple actions. So that's the challenge, like multiple actions, I repeat, simultaneously, and not only like you recognize the actions, but also how you localize. So in a frame, let's say multiple actions are happening. For example, I'm talking and also I'm like moving my hand. How in a frame I can exactly localize like these two actions. The third example is again from a slightly different domain of surveillance. So here, as you can see, this is a figure from this different data sets, and the work was published in Pattern Recognition Letters. So this is an interesting problem which is called person re-identification problem. So let's say a room has like two doors, and then a person has entered like or for a premise, like person has entered through one door, and then in between you don't track the person, okay? But then the person has like changed clothes, he has like different gaze, different gaits, and then the person is leaving, right? So can you find out really, right, that it's the same person? So it's a person re-ID problem. Finally, this is an example from this neuromorphic vision which I was mentioning. Like this was published in an ICCB workshop on. It's a very interesting workshop where graph signal processing meets computer vision. So where from the event camera you track like the moving objects. So we are trying to detect really the moving objects from the event cameras, and we are just showing comparison with different methods. So these are like here are some members of our group, like mostly the PhD students or the students who have just completed their PhD, now being postdoc in different parts of the world. And we do have a lot of international collaborations. So these are some recent international collaborations, like with Professor Natasha and Professor Enrico in Italy, then where we have been working on zebrafish imaging, and we have published a couple of works there. Professor Falcao in Brazil, where we worked on superpixel segmentation. So the picture which I have shown a couple of slides back, where we were localizing the actions. So if you want to really precisely localize the actions, then you can use the superpixels. For a lot of works, you can have the superpixels. And then Professor Thierry in France, we are doing moving object detection from event camera. And we have started work with Professor Dilip and Professor Krishna here, with the goal of structure detection from point clouds. So what we want to achieve in this this talk or this journey over the next, let's say, 50 minutes or so. Okay, so as I have mentioned, so we use many seasons, which are really different stages of computer vision for cancer detection. And the different stages, as you can see, this autumn is the classical. Then we have a gap for deep learning to develop. Then we have spring, where we have both classical and deep learning based solutions. And then we have really the rainy seasons, which is basically only deep learning. And as far as cancer detection is concerned, again I have mentioned, so we'll focus on lung nodules and brain tumors. And we will focus on segmentation. So by segmentation, we mean extraction of these objects of interest from a 2D image, or let's say 3D image volume. And we will see that there will be very low contrasts. There will be a lot of artifacts. So there are a number of challenges, variabilities in shapes. So how do we really detect or segment? And then the other challenge is the classification. So in the classification, I have just shown benign or malignant, but then we also have multiple degrees of classification. Let's say to what extent it could be malignant and so on. So we will also try to address these questions. Okay, so here is our in the first season, which is I just had a typo. It should be an autumn because it's fall colors. So this is not spring. Sorry, so we'll come to spring. So this is an autumn. And then let's see so what we do in autumn, or what happens in autumn. So we have beautiful fall colors. So this season is without deep learning, which is really now the buzzword in computer vision pattern recognition, where we cannot really do much work without the help of deep learning, right? So this season still it survives, and it has its own interesting features or aspects. So it still unfolds in front of us, a lot of hidden treasure. So we can solve problems using graphs, hypergraphs, and then different types of geometry, computational differential geometry, Bayesian approach. And we can use some classical ML techniques like decision trees, random forest SVM, but typically we can still do a decent amount of work without deep learning. So an autumn problem to start with is a computer vision based cancer detection is the general theme, but we want to talk about lung nodule segmentation using level sets. So this work was published a couple of years back in IEEE Signal Processing Letters. So here is the motivation. If you go to the statistics, you will see, and this is statistics from American Cancer Society, that that early diagnosis of pulmonary nodules, they can significantly improve the 5-year survival rate, and this lung cancer is really a leading cause of cancer-related deaths. So we want to segment nodules here, and you immediately see some challenges because you see a lot of variability in shapes, right? You have solid, part solid, non-solid. You have juxtapleural, juxtavascular. So there are a lot of variabilities in shape. So the question is, and also the position of the nodule. So the question is, can we develop a single framework, a unified framework to detect these different types of nodules? So which seems quite a bit of challenge. So there are some existing works on lung nodule segmentation. In fact, there are quite a few. But what we have seen or what we have observed was like we don't have like frameworks like which try to address segmentation of a large number or a variety of nodules. So they maybe are focusing on very specific types of nodules, like let's say solid or part solid and so on. So so that's like I think one of the main things like which motivated us. Though there are like techniques they can solve like typically one or two types of nodules. They can extract, they can segment, but they cannot really segment like all different types of nodules. And so what we did was like and so this is like the the contribution. So we developed like a level set framework to segment 5 different types of pulmonary nodules. And we will have some slides on level set. So we need to generate like, or we need to develop like a better level set energy function. And the two main aspects here are introduction of a new contrast term to handle like the low contrasts, and also the introduction of a new shape term to deal with like varying shapes of the nodules. So in computer vision, like as you can see that recognition of objects like it's really influenced by the particular shape of an object which is visible in an image. So the journey of level set, the evolution of level set started like after like we had this kind of active contours, like just to give you a brief idea. Like, so it's like a kind of a rubber band. So you kind of initialize, let's say, on an object, and then you ask it to grow, right? So there would be like essentially 2 types of forces. Like so, one would be the attraction of this like initial boundary towards the boundary of the object. So that would be like an external force. The internal force would be like this rubber band like which you like try to grow. So that should not be torn, right? So there would be like internal forces which would preserve the continuity. So with this, like we started what is known as an active contour, and then this active means like this contour is growing, it's moving. So that's why the term active. But then there are problems like if you take like applications, let's say in cells, for example, like if you have this biological processes of, let's say, like the cell division or like the cell merging. So you have like like an object breaking into 2 parts, 2 objects, or 2 objects merging into a single object. So you have to deal with the topology. So so level set is like a technique like which can follow like shapes that change like the topology. So as you can see, for changing topology in 2D or changing topology in 3D, like the level sets emerge as really a very powerful tool. So here are some basics. Like as you can see that there are like this level set functions like which is kind of growing, and then you have this phi function which has like this both spatial and temporal arguments like x, y, and t. And if it's on the the level set, like it's like you have denote like whether it's on the level sets, it's like within, it's outside. So for that you use like sine Euclidean distance, and with time like you can have the level set grow. So here's another example. So the 0 level set is is denoted by blue, and then you can see that like the 2 level sets grow and kind of like merge like here. So in that way, like it can handle like if there are some merging or like splitting. So initially, like in the left figure, you have 2 level sets, but then they can like combine and can merge. So if you think about like a level set, so there would be an evolutionary equation, means like the way the curve evolves, and then that's evolution equation for this 0 level set is given by Pocher-Chettian, like is this phi t is plus f grad phi is equal to 0. So f is really the speed function which drives the level set like to its intended contour. So here for our example, we have an initial level set which is denoted as by Gaussian, and then where like the reason to have it Gaussian is like so it has higher priorities to lung nodules because our goal is to denote really the lung nodules, and then it has like fall off priorities like for the other associated regions, means which are really not non-nodules. And in the energy function, like so the way the level set curve would grow, so it would be governed by an energy function, and then there would be really like a evolution in terms of like the phi, like del phi del t. So the energy consists of like different terms. So we have introduced like a contrast adaptive term and a shape term, and we'll talk about like how we have done that. But this distance regularization and this variance regularization, these are like the usual terms in the level sets, but then we modify really the contrast and shape term like for the specific problem. So we have this contrast adaptive term, and again without going into very details of the mathematics, like so again so this h is the Heaviside function and the symbols are defined. But like what is interesting is like how we really develop or design the contrast adaptive term is like if you look at these images, you will see that there is a background, and then you have really the portion of lungs, but then within portion of lungs, like within this like green circle, like you have actually the nodules. So its contrast is quite different from the background, but then its contrast is not so different from the other parts of the lungs, right? So the question is like how you can capture like these characteristics in your contrast adaptive term. So A, as you can see, is the ground truth, and then we have this is like some examples like where we have this output with our proposed contrast adaptive term, like which takes into account like this. If you look at the C phi function, so it takes into account like these three intensities and try to develop like a function. On the other hand, like if you have like a typical standard like contrast terms, like that's not going to work. And then if you exclude really the contrast term, then you can see also the level set is really coming out of this actual nodule. So it would lead to like an over segmentation. Then there is like the shape term. So how you really develop the shape term. So we used like a term, or we developed a term, a weighting term, like based on the circularity of the evolving contours. So this is a synthetic diagram. Like so, the way it's designed is like if this sky is giving it takes into account like the variability in shape. So if it's really like the circular shape, or if it's really the non-circular shape, like it will automatically get really the priority based on the computation of this numerator and denominators. So there is like this weight factor, like which controls like the speed of curve evolution, and then this this takes into account like what type of the shape the nodules like give. Now the final energy function, like it will have its like distance regularization, it will have its like the variance regularization, and with that it will also have our new contrast adaptive term and the new shape term. So we have a functional form of like this energy, and then you can actually do this energy minimization through the gradient flow, and you can compute like the del phi del t, and you can see like how the energy is minimized. There are more details probably which I will not go into it, but if you are interested, we can definitely like discuss later like how it will work, like the gradient of the contrast term. And the level set should also preserve like this the sign distance property, like which I mentioned earlier. So here are some experiments like which shows that on synthetic images it's preserving really the sign distance property. So for experimentation in this case, like we have this publicly available LIDC IDRI datasets where we have this as the total count of nodules, and then we use like the following performance measures. And here is an ablation study. Like so, as you know, like so ablation study is like we enter into a room and which has multiple switches, and we require all the switches. So what happens like if one of the switches is turned off, like for example, like heater turned off or the light turned off, so we'll see like the overall comfort falls. So here in the same in drawing by the same analogy, we will see that this dice coefficient like this is gradually decreasing, like as compared to like if all the terms are present. So if you drop like different terms, like you will see they have like the impact on the overall result. So you have the results like getting decreased, and this decrease is indeed significant. Is that you can actually conclude, or you can show by computing the p-values, like by showing that slow p-value. So here are some examples like where we show that that how like the different terms like affecting the evolution of level sets for segmenting like this, the lung nodules. So as you can see in the first column, like we can see like if the contrast term is absent, the second column is the shape is absent, and in the third and fourth, like the distance term and the variance terms are absent. So of course you can see that, and then the final one is like all the four terms are present. Naturally, you can see like in the first and second column, like which are our main contributions here by designing like new contrast and new shape terms. The deviations are more. So if you take these off, like then you have like more worse results, which is also reflected in the values of Dice coefficients as compared to the distance and variance regularization, but they are needed as well. And you can see like you can compare just with the ground truth, like with the each of these results, and you can see like which is also qualitatively matching. So the qualitative, the images and the quantitative values, they corroborate really the same thing. Again, like which we have shown here that this is like robust to initialization. So you don't really have to initialize it. Well, I mean, if you initialize like outside, its object of interest, then naturally it cannot really get there. But it's not that you have to do it really exactly at the center. So you can do it like at different points, and you can see like it will still go to find really the object of interest. Here are some visual results with other existing techniques. Some of them are here in this case are level set based, and you see like our proposed formulation like that gives better results. And this is also again corroborated by the quantitative comparisons with different existing methods. Okay. And in this slide, like we are showing that, remember our original goal, like from where, we started addressing this problem, that we have different types of nodules. So the question is like how really it performs on different types of nodules. So we have the solid, part solid, non-solid, juxtapleural and juxtavascular, and you see that really like the Dice coefficients are kind of quite comparable. So it does well on like different types of the nodules. Like on the other hand, like if you see that some of them you don't find methods like which have done on all the types of nodules, and furthermore, like even if you see like for example this method or this method which is like closer, like still they're doing on three types of nodules, but then still our results like surpass them. So even doing on like few types of nodules, like they could not beat like what we have achieved. So this is again like robustness to initial contour. Like so here we have shown like a unified framework for these 5 types of pulmonary nodules, and then what we have observed, like for not only for just this particular problem but in general, that accuracy of classification cannot be improved beyond a certain limit. So and especially if you have really multi-class classification, the challenge is more. Generally in a pattern recognition or in computer vision problem, like you have to find out really the attributes, right, the descriptors, and then you probably take an inference like, okay, in which class like it belongs, like for a classification problem. The segmentation problem, like which I just discussed, can also be thought of as a classification problem, because you can simply ask the question whether it's a nodule or not, right? But like the question becomes like, what would be the attributes? What are the descriptors with which like you are going to make these decisions? So it has been found that if you have really using deep features, like which we are going to see in a moment, then that would also help really in the inference process, like the final decision making. So I mapped this in 2 as like the winter. So this is kind of like a gap really, where like we wait for like more deep learning techniques to evolve. So a season where like deep learning techniques begin to flourish, and then we have very highly accurate feature representation, and which are like hierarchical in nature. So what I mean by hierarchical, like we can show like, and then we have associated like accurate inference. We have like various architectures. We have like this the different loss functions. So as I said, like if you have this traditional pattern recognition systems, like they're, the main bottleneck would be to use these handcrafted features or attributes. So what we need is a better descriptor. So in general, it's like very tedious, like if you want to develop these handcrafted features. So and often the problem is like from one application to other application, like this will vary. So we don't have like a general representation like to use the descriptors or attributes. So deep learning seeks to this learn features, like it provides a good solution through multiple layers like within a network, and which we are going to see. So here is an example like of deep network where you could see that there is an input and there are like multiple layers in a face recognition problem, and then finally like you have an output. So multiple hidden layers like through which it can process like hierarchical features. So each layer is represented as as a series of neurons, and then you have through the number of layers like you learn like more features. So this is an example, as you can see here, that initially like at the very left you have this low level features, right? So if you go like in the next layer, so then you learn like the mid level, and then finally like you have the high level features. So layer wise you try to like learn more and you have a better description. So very popular deep network is like CNN, though in our next subsequent parts of this lecture, like we'll talk about also different architectures. But like to start with this, the CNN is a convolutional neural network is a deep network like where like it has this input image, and then it can like assign really important. So that means in a layer we'll have this learnable weights biases, and then finally like you can do classification by discriminating between like different object classes. And this is generally inspired by like the way we human being used to recognize like the patterns. So here is an example of the convnet, like which can transform like you have a 3D input volume into a 3D output volume with like the different stages. And generally in a CNN building block you have many layers. So for example, you have this convolution layer, you have like this ReLU layer, which are activation functions. Then you have pooling layers, and you have a series of them. So you have like convolution, ReLU, pooling. Again, you have a convolution, ReLU, pooling, and then you flatten, and then finally, like you have this kind of like softmax layer. So let's say here the problem is you have these different classes of objects. So the softmax layer will give you the probability to belong to different classes, and then in general you take like the maximum one. So it will give for a particular object like the probability of that object to belong to all of these classes, right? Hence, like if you sum it up, those probabilities would be 1, and then you take the one which is kind of maximum. So next comes like our third season. Well, so we started with like an autumn. So again, sorry for the typo. So that was not spring, that was autumn, where we used like level sets, purely classical solution to segment, to extract like different types of lung nodules in a unified framework. But then we discussed that like we hit a roadblock because we need to increase like the classification accuracy. Like the task could be like more complex, and we need like better representations. So we have like the deep learning, like basic deep learning. So now at this season, like we have the classical tools, and we have really also the solutions from deep learning. So it's like the blossom of many flowers, right? Like, so can we combine them? And we'll again take a typical example. So what happens in spring is like a season where what I have just said, like many flowers blossom, right? So new enthusiasm, right? Like this computer vision or pattern recognition, like get empowered by the developments in like the deep learning. And so can we combine them to get like good results? So with this background, like we have a spring problem. Again, the goal remains same: computer vision based detection of cancer. And now we'll focus on like segmentation of brain tumors with deep learning and graph cuts. So this work was published in and presented in this EMBC conference just like a few months back. So the motivation is demarcation of tumor margins is challenging when the lesion is diffusively illustrative. So let me show you an example here. For example, if you see this figure, you can see again this tumor which is having very similar contrast. Well, I mean, definitely you can ask a question whether the levels it will be able to solve. It's a good question. And for this particular problem, we haven't really tried the level sets, but we felt that we could probably exploit based on both worlds, combining this deep learning, and there is a classical technique which I'm going to discuss now briefly, and some of you definitely will be familiar with that, is graph cuts. So how can we mix really the deep learning and graph cuts to segment this tumor? But here, the challenge is also more, because in this case, for this problem, we are showing that the segmentation in 3D. So this image is like an image volume, and then from the volume, we want to find really a kind of spherical blob or something, or a near spherical blob. So which is having a similar contrast with other parts of the image. So a shorter, but accurate way of identifying tumors. So, I mean, why we require this is so we want to have, early detection or early diagnosis. So here, if you look at the contributions, so what we have done is there's a classical, technique for segmenting images, which is known as graph cuts. The paper was published in ICCV, famous conference in computer vision in 2001. So where they Wycombe and Julie described really the segmentation process as equivalent to a max flow mean cut network, and then they showed that you have again energy optimization when you have the accurate segmentation. And then we have also this unit, which is not really a CNN. We'll talk about that. It's called an FCN, a fully convolutional network, and we'll briefly mention what's the difference between CNN and FCN. But then this unit is again a very famous deep network, which was presented by or published by the Ronen Berger in the MICI, which is the flagship conference in medical imaging, medical image computing, and computer assisted intervention. So if you go back, though the architecture of this unit, which we are going to see, is a little bit different from the traditional CNN. But the idea is if we go back to these few slides, where we showed this the probability maps. So let's say here the question we are asking is we have a voxel, which is a 3D version of a pixel, and the voxel, whether it belongs to the tumor or not. Okay, so for each voxel we will have a probability from really the this kind of softmax layer, and what we have decided to do is we'll not take the max at that stage, but on the other hand we'll use those probability maps to modify the existing energy function of the graph cut. So that's why I wanted to show this picture again. I mean, or this architecture again. So as you can see, the probability maps of a voxel belonging to the object, which is really the tumor, and the background. So these are the two classes, and then we used to derive new expressions for the energy function of the graph cut. So I'll just very briefly talk about the expression for the graph cut. So this is in the input to input MRI. So we are dealing with an MRI image here. So we have a 3D weighted graph, and then generally the graph is constructed in this manner. So you have each voxel as a node, okay, and then you have to construct really the edges in the graphs. And generally in a graph cut you have two types of edges. So one is for each of your classes, for example tumor and background. You can think of in kind of a hyper node, and then you connect all the nodes, all these voxels, which are the standard nodes, with this hypernodes. And then you have, so these are called the tiers, the terminals. And then you have what is called the neighboring links. So you connect really the with the voxel its neighbors. So that's called the end links. And the eventual goal is you will have, I will show you, you'll have an energy function based on this construction, and you want to optimize this energy function. So if you forget about this deep learning part or the unit part, you will have a graph cut model, and then eventually when your flow is maximized, then you will savor one of these ties for each of the voxels, right? So one of the, these T-links will be severed, right? So then eventually you will have for each of these voxel, a class, like in which class it will belong, like whether it belongs to an object, whether it belongs to a vector. So what we have done is like we used, and then, okay, so maybe we just I'll talk also briefly about unit as well. So as I said, like this is FCN, it's different from, CNN. The main difference is, without going into very details, in CNN you will have like this fully connected layers. So if you have fully connected layers, then you have to deal with a lot of parameters for your, the segmentation part. So what you do is like instead of, using like this, fully connected layers, you have a lot of like, multiple, like kind of, let's say 1x1 like convolution. And so that like you have a number of like, the convolution layers, like, the convolution connections, and then you have like, get away with dealing with a large number of parameters. So that's really the basic, the difference. And here are some details, like you have, something known as like a, a contraction path, and you have an, the expansion path, like which is done, respectively during the encoding and decoding phase. So here again are some details, like if you are interested, like so for the contraction you have this, you ask the question what, and for the expansion you ask the question really where. So the localization and voxel classification, as you can see that there are like, multiple like, like small, convolutions, like instead of like fully connected layers. And the important thing to note is that you have the total number of parameters, which is, why like the deep learning training using deep learning is much more computationally intensive, but that's much less compared to like the other standard like deep network like AlexNet and VGG16s. That's why like this became a very popular model. So what we did is, this is the defunction of the graph cut, and as you can see there are like two terms. So one is called like the data term. So this data term actually establishes the strength of the connection of each node with this. So these are like basically like this strength of like T-links. So strength of connection or affinities of each node with is this hypernode representing a object, or and hypernode representing a background, and or like an hypothetical node, you can say. So that's the better way to say. And then you have this like the smoothness term, like which tells you that a pixel should be influenced by the characteristics of its neighbor pixels. So you have to weight them, you have to scale them like using lambda. And in the original paper of Boykov-Joly, they use the same lambda for like all pixels. But then what later on, also in earlier works we have done, other people also have done, but we have discussed and we have decided that this lambda can vary between depending upon the location of a pixel. So think about a pixel which is really within an object class, right? So then, or within a background class, then there's more influence of its neighbors rather than because it's well decided like the class. On the other hand, like if it's probably in, let's say, near the boundary or edges, then you have more influence. You have to be careful that it doesn't get misclassified, and probably to really less influence of its neighbor terms. So in that way you can decide lambda to vary. So in this case, like we have derived like different expressions for this data term and smoothness term. Again, I'll skip the details of the mathematics, but just like the philosophy. And we have also, as you can see, like the smoothness term modification. We have like here the data term modification, and then we have the weighting parameter modification. So this lambda also varies, and all these modifications are done based on this probability map of the unit. So that's like the kind of synergism. And then you have like a new kind of deep graph cut model. So you have this BGC lambda, BGC, or BGC. So this is the algorithm, and again, like we use this PRAX 218 dataset. Here are the results. Like you have this. So this is, you can see as an ablation study, like that's the ground truth. And if you use like only unit, what is like the dice coefficient? If you use only graph cut, what's the dice coefficient? If you combine the deep graph cut, what's the dice coefficient? Again, the qualitative result, like as you can see, this this D resembles like A much closely as compared to like B and C. So the always like qualitative results corroborate with the quantitative results and vice versa. And again, here there are some results, some comparisons on standard methods, like where shows that we are being better. Even like if you use the standard Birkhoff-Joule, it seems like the contrast is a problem here. It doesn't do that much. And then we have also shown that if you use like the different terms, like such as the only data term, only smoothness, data and smoothness, and so on, like what happens. And here it's a comparison with like the other methods on different parameters. Some details on the implementation. And so this detection, delineation, and characteristics of 3D brain tumors using MR imaging, and theoretically speaking, like we have combined like this graph cuts with UNet to have like better results. And here is some like more things to do. Now I come to the our final season, which is really the rainy season. Again, you think about the journey. Like we started with autumn, classical solution. Then we waited for something to happen, like there were like evolution of deep learning techniques in winter. Then we had spring, where we combined like this deep learning and classical solutions. But then we see like we are getting more and more overwhelmed. I don't know whether overwhelmed is probably the right word, but it's more and more deep learning. Right? So the deep learning kind of reigns. So the first problem of the rainy season, like I'll very briefly discuss like two problems and then we'll open it up for discussions, is the classification. So again, we are solving a little bit different problem. So far in the goal of cancer detection, in the path of cancer detection, we have solved like segmentation problem. Means extract object of interest, separate object of interest from everything else, which is like nodules in case of like lung nodules, and tumors in case of like brain tumors. Also, we had the CT images in case of lung nodules and MRI images in case of brain. So here, what we want to do is we want to classify like brain tumor, and we will see that we'll use like a different modality. So we'll use radiology, means like we'll use MRI data, but we'll see that if we want to do like a very detailed classification, then MRI by itself cannot or is insufficient or cannot do well by alone. So we'll also have like this histopathology data, and this was published like shortly before like in here like at ICPR, though it was like presented virtually. So it was like presented, but like this proceedings is not yet out, so it would like to appear. So the motivation is like we want to have look at like the gliomas, which are really the primary malignant tumors, and we will show that like just if you want to use MRI data, you cannot have really the detailed classification. So MRI alone cannot provide like the detailed depiction of gliomas. On the other hand, like if we combine like this MRI and histopathology, so in histopathology, like this glial cells can exhibit certain like morphological features which can be captured by this whole slide imaging, and then you can combine both of them to take like important decisions. So the contributions are like we have like a 3D CNN model for post. So this is like the basic CNN, so 3D CNN for post classification. So here we take the decision like if it's glioblastoma or like a non-glioblastoma. But if it's non-glioblastoma, then just based on MRI, we cannot conclude that it's like astrocytoma or oligodendroglioma. So it has to be some other modality. We have to analyze some other modality to take this decision. So for that, like we use whole slide imaging using like 2D CNN. Like so, you have a slides like WSI will have some pictures, and we take like features at different magnification levels, and then employ like this graph convolutional network for fine classification. So this is like a coarse to fine classification. So and the interesting part is like it's like part of this contribution that how you build the graph. So the GCN, there are like the standard ways like how you have the layers, but then so what would be the graph? So how you build the graph in GCN so that like you have better impacts, and we will show that there are different ways you can build this graph and make your graph more informative, so that the eventual graph convolutional network like will pay rich dividends. So this is for the post classification stage. So we have a 3D CNN model, and we take a decision like whether it's like glioblastoma or non-glioblastoma. And then for the deep feature extraction stage, in case of like the WSI images, that you can see that we have a deep feature extraction model, DenseNet, like for WSI. But then you take these WSI images at different levels of magnification for like this local and global features, and then you try to kind of combine them. So how you really concatenate the features, which will be your nodes, are like you take like this local and global features. Again, I'm skipping the very details, but like the idea is how to build the graph. So what would be your nodes, in which space you want to build the graph, and then like the node embedding. So this is a very interesting part. So generally, like the way we construct graph is by taking like really the feature similarity, right? So you take like two nodes and then you find like the similarity, and then can apply some kind of kernel. So here, for example, we used an RBF kernel to show that if like let's say this factor is greater than certain threshold, then you put the age. So you really do not want to connect everything with everything and build a complete graph. So the connections are dominated by really the this RBF kernel. So this is probably a standard way of doing based on feature similarity. But the question is, can you incorporate some other things? Well, the answer is yes, and then you can look at like the graph topology. So since like we have the level information of some of the nodes, like which classes like it belongs to, that's really the part of the ground truth. So you can use that information to again set the ages. So there you use like you can found some rules which we are showing in the next slide, and you can check with the probability of a node to belong to a particular class, and then you can figure out like some rules. For example, you can so you have some level nodes and some unlevel nodes, right? So the two level nodes are connected only if they belong to the same class, and then you have like a level node and unlevel node. So how you connect them, and then you have like two unlevel nodes, like how you connect. So an unlevel node is connected to a level node. So if you have the probability, you can calculate like belong to a certain class, which I just shown in the previous slide. It's above certain threshold, right? And then how you compute, how you connect right to unlevel nodes, right? Well, so if like you can calculate the probabilities of these unlevel nodes to belong to certain classes. So if like if you look at the difference of these probabilities, and if they are kind of comparable, that means these two nodes are having similar behavior, then you connect. So in that way, like you can frame certain rules, and then you have the the ages, right? So you have this is really the the spatial connectivity, which is driven by topology, like the distribution of like levels among the nodes, some of the nodes for which the level information is available. So if one of these conditions are made, then you put it one, like you connect, otherwise it will 0, and then eventually you have an adjacent symmetry. So either it's driven by feature similarity or by topology, and then you have like the standard like graph convolutional like network to to have the classification. So this is the flow chart. As you can see, that if you have like 3D MRI volume, and then you do the box CNN, then you have the question like it's glioblastoma, yes or no. But then if you have no, then this MRI will not be able to help you, right? So there comes the role of this 2D histopathology, and then this 2D histopathology can also tell you like the final classifications. And mainly we are interested in this astrocytoma and oligodendroglioma. The data set we have used for this is again publicly available data sets like CPM, the RAT path, like which consists of for the data we have to have this paired MRI scans and WSIs to have. Otherwise, like we cannot really do the experiment. So I believe some other challenges would be, let's say we have MRIs for some and WSIs for some. Then can we apply some sort of, let's say, transfer learning probably to again have the same kind of model work? So I believe those could be good potential problems. So here are like some more details of the data, and here are some more details about like the implementation plan, and here are some results. Like once again, like if you have this only MRI, only WSI, and for the graph, like as I said, like only feature similarity, only graph topology, and all of them combined. And as you can see, it's again like an ablation to just understand like all the components of our solution are working. I mean, they may not contribute equally, but then, I mean, they should each of them should contribute to a reasonable extent. And then if you have like all these combined, then you have these results as you can see here getting improved. And here are some comparison with state-of-the-art methods where you have this F1 score, coherent stop and balance accuracy, and as you can see, you can from here you can have the results and some of them have reported some of the metrics, so that's fine. So with that, so this discussion, for this particular problem, we have shown a coarse-to-fine classification of the MRI, of brain tumors using MRI and histopathology data. And for MRI, we have this Foxian and this coarse classification, and then you have this GCN for further fine classification, and demonstrated that you can with a better graph for GCN, graph convolutional network. I haven't included any slides for the way the GCN works, but that's standard. So using feature similarity and graph topology, and then we have this the results. So a long list of acknowledgement. I started with an acknowledgement. So Professor Majumdar, she was a professor in this Cancer Institute in Kolkata. So we collaborated on this lung nodule detection. Professor Tiwari is in Institute of Neurosciences. So for the brain tumor problems, we are collaborating. And this Orijit is currently the PhD student here. Rukmini is past PhD student. So I mostly focused on their works because they worked on biomedical problems. Rukmini is a postdoc at MD Anderson, and other members of my group. We have many collaborators, and I'm really fortunate to be associated with many brilliant people across the world, cutting the boundaries. And so my thank goes to all of them. My university for providing the infrastructure and internal funds. We have industrial and sponsored research scholar programs. We have from the government of India doctoral fellowship programs, and also the different travel grants with which I can meet a lot of people and enrich myself. So with that, thank you very much. Takshkal Duha, and for more information, please visit my site and my group site, and I'll be happy for questions. Thank you.